Thanks for having me here. It's really an incredible honor and pleasure to be here to deliver the Brazel Urban Climate Lecture. I want to thank Matt and Barbara also for all the organizational work that they've done to make this really smooth. Saw some incredible poster presentations from students from a lot of the faculty here. So just want to say thanks for giving me the chance to talk to you a little bit about the work that we're doing in New York and the work we're doing at the Urban Systems Lab. I'm going to start a little bit broad, and then we're going to zero in on some of the things that we've been doing in New York as some case studies to really think about climate risk and resilience in cities. And it'll kind of take this form, starting with a sort of broad view of the urban planet, thinking about the sort of systems nature of cities that we're trying to work with, understand, and transform, both for adaptation, resilience, and other things. And then ending with a new project that I want to tell you a little bit about that I think has the chance, not just this, but in general, this kind of approach to really transform our urban climate science. So I'm going to start here for a minute and tell you just a quick story about where we've come from as a way of thinking about where we are right now. You probably know some of this, but during human evolution, Earth systems went through some really wide temperature swings on the left, right, for multiple 100,000 years. And humans are evolving during this period. But then we had this cold phase in the Pleistocene, and then we entered this 10,000-year period of relative climate stability, the Holocene, right? During the Holocene, this really allowed the agricultural revolution and then the industrial revolution, and I'm going to argue the urban revolution. And the urban revolution is the one that we're seeing this co-occurrence with all of these accelerating signals that we have on the planet, which I'm sure you've seen a lot of this before, that moves us into human domination of the planet, that ushers in the Anthropocene, which I know is a debated term in a number of ways, but this is this epoch that we're now able to really document very clearly the human influence on fundamental Earth system processes, ones that are now measurable and clearly, in a lot of ways, inescapable. And a key human signature that we see in the upper right here is the planetary scale warming that is happening on such a scale and at such a rapid pace that we appear to be threatening the stability of the Holocene, right? And I'm setting this up so we can really start to think about what is our job in the urban climate space when we start to think about how these curves not only should bend, but need to. Because we've dramatically altered the Earth systems, we're seeing a number, and I'm not going to go through them, but a number of tipping points in Earth systems all around the planet, this crossing of planetary boundaries. And then what I really want to discuss with you today is the shifting of the climate in the ways that we're already starting seeing. And we're seeing this largely through extreme events and extreme weather, the way in which the climate signal is increasingly strong through storms, various types of coastal storms, heat waves, droughts, fires like we've recently just seen, and even Arctic blasts. I just flew down from Maine, where when I got on the plane yesterday morning, it was -10. Sure, it's just a winter, but we're seeing some real dramatic shifts in the Arctic fence and the AMOC and other parts of Earth systems that suggest that we have this fundamental question about where are we going from here, right? What is the climate risk that we're going to need to adapt to in the future? And not only the near term, but the longer term. And I would argue that in the last 75 years, largely since 1950, we see that these changes are concurrent and really strongly correlated with planetary scale urbanization. You've, I'm sure, seen the great acceleration curves. Scientists have recently released the blue acceleration curves. One major pattern since 1950 really stands out, which is that this acceleration and growth of cities and the spread of cities around the planet, not only just the spread of urban land area, the spread of the urban population, but the resource consumption that's associated with urbanization. All of this moving towards a transformation towards an urban planet. One could even call this urban revolution, and just to be a little bit cheeky, the Urbocene. And I'm doing this on purpose to really try to help us understand how important are cities to the transformation of the planet, and especially when you start to think about planetary sustainability. Just to put a few numbers on this, the urban acceleration has meant that now over 70% of economic growth in cities is happening in cities, 70% of global energy, 70% of carbon emissions, and these are probably, makes a lot of sense even just from a simple outlook, if you extend those curves, that increasing urban dominance on the planet means that we're going to move towards not only 70% of people living in cities by 2070, but those other numbers increasing as well in terms of the urban influence on the planet. So it's not really a stretch, I think, to imagine that the urban driver of planetary social and environmental change is not only going to continue, but it's going to be increasingly dominated by what I call the 3 Ds. How we develop our cities, how we devour or not resources, and how we make decisions in cities. So the question trying to address, not fully in this talk, but for us to think about here is how can we fundamentally transform the urban development paradigm towards climate resilience, but also equity and sustainability. And so there's some ideas here in this book, which I invite you to download for free if you're interested in some of that work. But depending on any type of city that you live in, whether it's here in Tempe or in the Phoenix region or other places around the world, you can probably all tell a story about how transforming systems, and I would say that's the structures that underpin some of our toughest challenges, some of our most wicked challenges, that transforming those systems is actually really difficult, right? And it's difficult because cities are complicated places, they're complex places, they're very connected, right? They're connected internally, they're highly connected externally, they have networks of infrastructure, of institutions, of ecosystems that are dynamically interacting in real time, and they're producing dynamics that are desirable in some cases and undesirable in other cases. They're also increasingly congested spaces and contested spaces. During our work for the IPCC, for the last assessment cycle, it's become increasingly clear that the nature of climate risk is changing. And it's changing in a ways that's becoming increasingly systemic, increasingly simultaneous, and in ways that's leading to cascades across the number of subsystems within the urban systems, right? So how can we make sense of this complicated, entangled, and even complex systems? Mike Chester, who's here at ASU, and colleagues have some ideas about this, so I'd invite you to read this paper because I think there's a lot of interesting work that's not just coming out of ASU, as it does, but others. But I would start with this. I'd argue that it's systems all the way down, and that this is fundamental for us to understand not only how we do our research, but how we advance practice in the space of climate resilience and adaptation. And what I mean by this is that a fundamental concept and a theoretical foundation for all urban climate resilience, mitigation, and adaptation efforts is to take this systems of systems thinking, which has been around for a long time, but hasn't been applied, I would argue, enough, take this very critically into our research and practice. And doing that, regardless of discipline, is one that recognizes that unless we're transforming in a coordinated way, with information feedbacks across social, ecological, and technological systems, that includes the interactions among these domains, which I know is a tall order to really kind of take in all of this complexity that's actually happening in real time in our cities. If we don't do that, we're likely to continue to see these trade-offs that we see more trade-offs than we see progress, that we see more sort of incremental transitions and less systemic transformation. And given the nature of the challenge, it seems pretty clear that we need really fundamental transformations to meet the scale of the climate challenge. So the SETS triangle, as we call it sometimes, or the SETS triple helix approach, is really just an attempt to help us think about the intertwined, intersectional, and highly interconnected nature of socio-ecological and technological systems in cities, and that if we can study these, if we can really learn to work with the interaction of these, and I saw some really interesting work with the students here in their poster work, really trying to look at the interactions between some of these subsystems and how they actually affect each other in real time, then I would argue we have the chance to actually bring about positive change. And yet, there is this like fundamental question, can we really understand this level of complexity enough, right? Can we understand urban sets enough to direct them towards adaptation and transformation, towards good Anthropocenes and away from these dystopian narratives that really dominate the way in which we often think about the future or are told what the future is likely to look like, right? Especially in news cycles, but not just that, the sci-fi that I read. Some of it's positive, but a lot of it's really dystopian, right? And our future scenarios tend to be this way as well. To that question, can we actually do it? I would argue yes, but I'm arguing yes because I think it's really only in the last 10 years or so that we've seen a massive data revolution that's put the wind in some ways at our backs to understand the complexity of critical system feedbacks and the ability to run scenarios to map out positive future trajectories. And additionally, we're seeing this increasing temporal and spatial resolution of Earth sensing systems. And all of this has brought us into the development of what we could argue is a new quantitative urban science. One that I haven't even touched on AI yet, and we will. We'll get to that in a little bit. But it's really changing our science of systems again because of the changes of not only the science itself, but the technologies that are providing data that allows us to start to make sense of that complexity. So just to illustrate this point, in New York City, this is just a virtual flyover in Manhattan, but I'll give you an example of this as where we've layered the social and ecological data into the built infrastructure of the city. And this is the kind of data that's being used to show indicators of social vulnerability, right? That's being used to target resilience investments. This kind of data is being used to understand climate risk, to provide inputs into atmospheric models, fire models, hydrological models, for understanding energy demand, for understanding transportation service delivery, right? You can ask a number of questions, and I think you could probably start to imagine what a true digital twin version of something like this for any of our cities could do for us if we can start to then ask in real time how all of these systems are actually interacting. And so again, the point here really is that the landscape of what's possible is changing dramatically, and it's changing kind of right now. So what I want to do is show you a few examples of how we're thinking in systems in some of the work that we've been doing in New York, how we're harnessing diverse types of sets data as a way to understand complex system dynamics. And in particular, really, I'm going to focus in a little bit on urban flood risks. So for the heat people, there is going to be a little bit of heat stuff in the rest of this talk. There's a little more on the flooding side as we move forward. And what I'm really trying to hope we do is to look at where can we take the science even further. Where can we harness the edge of technology right now so that science is keeping pace with other sectors in our society that are moving really fast? So let's talk a little bit more about climate risk. This is a recent stat that I just kind of stumbled on, and I found it really interesting to try to see how is risk changing in our cities. In a recent UN Habitat report, they showed that about 12% of cities that have been looked at since 1990 have changed their climate type, largely for warmer. And if you extend that out just another 15 years, it looks like it's likely to double, roughly, right? So that just kind of gives a sense of how dramatic some of these shifts are. In the IPCC work, the stat, and I'm probably going to give you one or two of these in the talk, this is the one that stood out for me the most, actually, when you get to the bottom headlines of what do we know about climate risk on the planet. And it's that the next 20 and potentially more than 20 years are already built into the climate system. So what this means is that we've been seeing this accelerating trajectory of climate risks. Right? We've been seeing increasing frequency, intensity, and duration of a whole number of extremes. And for the next couple decades, it's likely we're going to see more of that. Right? And I don't just mean more of what we have, more of the accelerated trajectory. So that's like the sobering thought, which is what is the actual adaptation that we need to have? What is the actual level of resilience that we're going to need to have, not just now, but in 5 years, 10 years, in 15 and 20 years, if it's already built into the climate system? Just after the IPCC report came out, all the urban authors got together and developed what we call the Summary for Urban Policymakers. And it really tried to distill down what do urban policymakers need to know about the climate science now. And if you haven't checked this out, you might be interested in this. This is also free to download at supforclimate.com. But I mention it because in there we summarize one of the key findings in the urban adaptation chapter from the IPCC, which is to try to understand what is the urban adaptation gap that we're actually facing in the present. And this is a little bit hard to see, but I'll explain it really quickly. And the red bars are the urban adaptation gap. And in each of the regions around the world, what you basically see is that is the highest income in the top bar and the lowest income in the bottom bar. And you look across a number of sort of questions about climate risk. What's the risk in terms of heat waves? What's the risk in terms of extreme rain flooding or food insecurity? And we've tried to map this out. There's a lot more work to do, but it's a starting point to ask the question, how big is the adaptation gap? And what is the set of strategies, policies, plans that need to be set in, actions on the ground that can start to close that gap? And two things kind of stand out. One, won't probably surprise you, is that the low-income and vulnerable populations have a much larger adaptation gap. The other that might not be that might be surprising or not, is that the wealthy also have serious adaptation gaps in a number of these regions around the world. So it just kind of goes to show you where we're at in terms of the need to really spur forward adaptation in cities on a scale that can meet the scale of the challenge. Now, New York City is a relatively, I'd say, well-resourced place, second largest regional economy in the world, but here too we have massive adaptation gaps. This is a storm that happened in 2021. Some of you may be familiar with the Hurricane Ida that swept all the way up through from the Gulf all the way up to the eastern seaboard. This was the worst rain event in New York City history. It dropped over 3 inches of rain in a single hour. That was just what was measured in Central Park. It actually got up to 5 inches in other parts of the city. This was sort of a classic cloudburst event, and it's really redefined the city's approach to flood resilience. Ida flooded basements, caused deaths, a lot of really horrendous impacts, including economic impacts. But one of the things that was really clear after the storm is that it hit low-income, minority, and immigrant communities the worst. Just 2 years later, Tropical Storm Ophelia, also in September, dropped 10 inches of rain in Park Slope, Brooklyn, and looked kind of like this. A fundamental question then really is like, not only where is it happening, how bad is it likely to be or already going to be, but how can we start to develop strategies that can protect against that? And so we've been looking at this question about vulnerable neighborhoods for a long time. I'll just show you a couple little examples of this, where we see disproportionate risk for vulnerable communities in the city in New York. And this is one example of some of this work where we found if we just do something even simple, but it helps like shine a light on the problem in the city so we can help to direct resources in the places where they need them most. We see that over 800 people that live in environmental justice areas are also living below the 100-year floodplain. So it gives a little bit of the sense of the question. And in New York, the real question I would probably put into two big areas. One is, how do we protect the most vulnerable from climate-driven extremes, like pluvial flooding from extreme rainfall? And how do we prioritize billions of dollars of investments just in New York City alone for maximum impact? Because we're going to spend it, we're going to have to protect our infrastructure and the economy and vulnerable populations. So where should we put it? That's the question New York has been facing and really kind of woke up to it when these storms happen. So as part of the New York City Panel on Climate Change, in the 4th assessment report, which we just released during Earth Week last year, the City of New York contracted a bunch of academic institutions, but also consulting partners on what we call the VIA project. So I'm going to dive into a little bit of some of the research here that we've been doing, which we led out of the New School. And among 4 major tasks that we contracted to do, and this was kind of a weird thing, is to try to do science faster than normal. And not because we're trying to get a publication out, but because we needed to provide new science so that NPCC could assess it, so then we could give it to the city, because the city is legally required to take that science into account in all of its decision making. And we really wanted to get a handle on what is the latest science on climate change. So the Flood Vulnerability Index was something we were tasked to produce. And I'm going to dive into it a little bit, but the reason that this was that the city asked for this and asked us to get together and try to produce this was because the cities themselves had come to realize that not only were storm impacts disproportionate on vulnerable populations, but the emergency response, the operations, the resilience planning, the infrastructure investments across all the major departments, across the Parks Department, Department of Environmental Protection, Department of Health, Office of Emergency Services, DEP, all of those groups did not have a tool that helped them to prioritize equity in their climate response. Didn't really have a tool that said, now we can change our operations, our emergency response in a way that the city has agreed this is our tool. And this is something I've found in working with cities, is that you can produce a lot of science and say, this is the tool you should have, but they need to have buy-in from the beginning, right? They need to feel ownership over it. And so we worked to produce this because DEP said we need a tool that we can use to prioritize equity and vulnerable populations in our day-to-day operations. And the Office of Emergency Management asked for a tool that they could use to prioritize emergency response during storm events. So we spent 18 months meeting monthly with all those relevant agencies, weekly with a core group of those agencies to co-develop an FEI so that when we handed it over, it was theirs. And this will seem, for folks who work on vulnerability, kind of straightforward. Like, wasn't that, it's not that earth-shattering, except we didn't have it. And I'm giving you this example because most cities don't have it, actually, right? So using Cutter et al., Susan Cutter's work on vulnerability, and overlaps with some of the work used in the IPCC in terms of defining vulnerability. And I'll just lay it out here for you. We have 3 components, right? Exposure to the hazard, the susceptibility to harm, and the capacity to recover. And I'll go through a little bit of methods just so we can talk a bit about the results and how they're being used. So here's a bunch of indicators. You could come up with a lot of social vulnerability indicators that are largely from social demographic and economics. So again, this, as someone who's done this for other cities and worked for a while, it wasn't so much earth-shattering in terms of what we came up with, it was the process. It was that we were co-producing this with the city, and in that process, we were able to come up with what we call the fishery index, and if anybody has a better acronym, I would very gladly take it, because it's a terrible one. But basically, this doesn't have exposure in it, right? And it has just those other 2 components of vulnerability. And we did that because there's many kinds of flooding. So we wanted to develop something that could work across multiple types of flooding. So what you can't necessarily see here, but I'll point it out for you, is that this is those social economic indicators developing a fishery index. On the right, we took hazard scenarios for different types of hazards: coastal flooding, tidal flooding, and pluvial flooding from extreme rainfall. Calculated the exposure to that based on residential units in each of the census blocks. And then inside that, we put those together and we created flood-specific event FEIs for each of them. And because you can't see that, I'll show you what they actually look like. So this is the exposure. So first we wanted to understand where is exposure higher or lower under different scenarios. And you can see different types of flooding. The current storm surge and looking at what that might look like under sea level rise in the current state versus the NPCC projections out to the 2080s. Similar for tidal, current, and 2080s. And actually 2 different versions. I'm just showing you the current one for stormwater scenarios. And then, like I said, we combined that exposure with the fishery index to produce a set of FEI tools. Again, I think this is important science, is important work to be doing. It's the kind of work that can be replicated. We've done similar work in Milwaukee and Yonkers. We're doing this work in Atlanta right now. But the real point is that this is the kind of work that actually can change the way investments are made. It's the kind of work that can change operations, emergency response in a way that really starts to pay attention to the question of where is this response and this investment needed most. And so now this was released in Earth Week. New York City launched their EJNYC mapping tool, which has layered actually something like 100 data sets. And when you load it, and if you're interested in this, just Google EJNYC mapping tool. The FEIs are one of the first things that come up. And so this DEP is using this. The Office of Emergency Management is using this, and others. So I want to tell you about another major investment that New York City made actually before the Ida storm. So we're going a little backward, out of order. This isn't chronological order. But when Hurricane Harvey hit Houston in 2017, you may remember, I don't know if anyone was around there, but you will remember some of those iconic images. That's the first time actually that New York City really woke up to the potential for extreme rainfall. This is before we had the storms I just mentioned. And the city has been so focused since 2012 and Hurricane Sandy on coastal flooding that's where it really put most of its investments. That's what it wanted to know more about in terms of the science. But when Harvey hit, the city said, what if that happened here? And so in 2018, the city contracted with my colleague Jennifer Charrier at Brooklyn College and our team to co-lead what was called the New York City Stormwater Resiliency Study. And we did a bunch of things. I don't have time to go through all of them, but we had a team doing extreme event analysis, doing a bunch of rain modeling, producing a whole range of scenarios. And there's a couple things I really want you to notice. One is that we came up with a set of scenarios that we thought were all important to answer the question around where is flood risk from extreme rainfall likely to be, under what kinds of ranges of rain events, et cetera. And so we had 3 different categories. One was chronic events, right? Happen often, but not that severe. Extreme events, rare events that have large inundation in terms of storms, and then compound. So we came up with 204 scenarios that we thought needed to be modeled. And the city's like, yes, we want 204 scenarios. And then in those little numbers that you can see, actually, it turns out it's computationally expensive to run these scenarios and to run all these hydrological models. So we reduced that down to 20. And then we realized that was too expensive. We reduced it down to 16. And then we produced 5. So we produced 5 scenarios. Those 5 scenarios, this is a $2 million project, right? We produced those 5 scenarios. And what we found was that water was being poured when you sort of put rain on top of these hydrological models and you let them route through the city, and hopefully they're routing in the places that make sense. You find that in some cases we had roads that were showing flooding in the models that didn't make any sense because it didn't have the drain in the road, and we knew the drain was there, and we knew that road didn't flood like that. Or it'd have 6 feet of water in a backyard, and we're like, that's not happened. We've been through some of these events. It doesn't make sense. So we spent a whole nother year, passed this off to Arcadis to do a bunch of post-processing. So now what we got is we finally ended up with 2 scenarios. So New York City launched the first of its kind, full citywide scenarios. They're now called the NYC DEP stormwater scenarios. I'm showing you one of them here. This was the extreme event. So we had 2 events, a moderate and extreme event. And in the extreme event, you can see this here. It's a 3.5 inch in 1 hour storm. And in the yellow or orange is a projection out to the 2080s of sea level rise. So you could also think about those 2 things together. Interestingly enough, and these storms were completed and released before the Ida storm. This is very similar to the Ida storm. So after the Ida storm, we were able to go back and see how well it did. And I won't show you that, but the model performed very well. So then we were able to bring this into a DataVis platform. And if you want to check this out at stormwater.nyc, you can easily do that as a way to help now ask those questions, going back to that sets framing I gave you of when you have these scenarios, you can overlay various things like the FEI that we produced later, also where critical transportation exposure might be. So now we could start thinking about not just vulnerable systems, but vulnerable infrastructure systems, not just vulnerable transportation systems, vulnerable critical facilities. Where are the hospitals? Where are the education facilities? How does the city have to be thinking about how to reroute in order for people to be able to pick up their kids from school and get home if they're taking the bus, or even to reroute cabs and other things? And all this really resulted in the production of the New York City Stormwater Resiliency Plan in 2021. Again, 4 months before the Ida storm that really devastated New York City. This was a landmark plan, first of its kind that we know of, first in the country to really focus an entire planning effort just around stormwater resiliency. And so in a lot of ways, there's been a lot of look at this as like a landmark start, and yet having a plan doesn't mean that we're prepared, right? 4 months later, the city was completely devastated by Ida, but it got us in the right place. All of that flood modeling and vulnerability work behind it and other things that came out of it cost the city, and I'm making this point because I want to move into the next section of the talk, but just to kind of remind you, about 3 years, about $3 million, and we got 2 scenarios out of it, and is a game changer. Billions of dollars are being invested because of those scenarios, because now we know from just those 2 chronic or moderate and extreme events how to think about rainfall in the city and how we can start to prioritize investments. And New York City is planning out that kind of investments in green infrastructure and gray infrastructure, social strategies, and many other things. But this is the question that I want to kind of dive into. What if we could produce all of that and a lot more faster and cheaper? What if we could generate 10 to 100 flood risk scenarios? What if we could do that in 10 seconds? And what if we could do that for $10? This is the game changer that's happening now when I say there's a shift in the technological advances that can allow us to really move the needle really dramatically. And so this is sort of the last piece that I want to dive into a little bit here, is that it's not just about speed, it's not just about cost, it's about who has access to this information. So New York City, well-resourced, has a lot of actionable information. This area, similar, but most places around the world that's not true. In fact, most places in the US, depending on how you count it, there's 5,000 cities and towns in the US. 99% of them do not have this information, right? There's 100,000 incorporated areas. All of them need to be doing resilience planning. If it's not for flooding from extreme rainfall, then it's to drought or it's to fire or it's to cold winter blast, or it's to extreme heat, right? There's a resilience planning needing for every single community, and yet there's a huge disproportion who has access to this information. This is true not only in the US, but around the world. Depending again on how you count it, there's about 1.9 million cities around the world. When we talk to ICLE, which represents 2,500 cities, when we've talked and pitched some of the work that I'm going to show you in a minute to the Global Covenant of Mayors, which represents over 13,000 cities, they give us exactly the same answer. They say cities have nothing. They have various types of data that they're trying to use, but they don't have actionable climate risk data where they can prioritize at the scale, at the local scale that's needed to really put investments in a place where they can be impactful. So those 13,000 cities, just with Global Covenant of Mayors, that's over 1 billion people just in those locations, that we could provide a tool to them that could spread, right? So this is not just about the global north, this is also about closing the risk gap. And so I want to tell you about a tool that we're developing that I'm pretty excited about, if you can't kind of see the build up to my excitement here, called Climate IQ. We've got some seed money from google.org that has allowed us to launch the development of a new AI-driven risk tool. And what it is in a nutshell is it is a mission to democratize access to hyper-local climate risk data for under-resourced cities and communities around the world. How are we going to do this? We're going to do it in a way that can be used hopefully for multiple types of users. So that's already a challenge when you have an audience that's really broad and not just, say, local planners in the United States or in large cities. But we're trying to meet needs across a wide variety. And the basic approach here is that we take an AI climate risk tool. It's built on latest science advancements, and I'll discuss this in a little bit of detail quickly, to really try to expose climate hazard in a way that has open access data, has customizable dashboards and APIs, so we can deliver it in a way that can work for a very not technically savvy audience, as well as those who really want to ask harder questions about this, and then to co-produce this in a way that we build trust and transparency along the way. So here's basically what it looks like. We're starting with flooding and heat. We want to expand to drought and air quality, but we're going to start here in producing this at high resolution. So 10 meters for rainfall, statistically downscaled for heat and humidity and heat index, also to 10 meters or so. And we're working on bringing future scenarios. So the stuff I'm going to show you is sort of the current state of climate risk. And the basic approach is this. We take machine learning that can analyze climate risks much faster, much more efficiently than traditional methods. And this approach allows us to do a couple things. It helps us speed up and lower cost. But what it also allows us to do is learn from data-rich cities like the city of Phoenix, which is a partner on this project, like the city of New York, which is a formal partner on this project, like the city of Copenhagen, who's an MOU partner on this project, and then learn from that, allow the AI to learn, and then we can distribute this for cities that we don't have that kind of data richness, because it's going to understand the complexity of cities. A little bit of how it works, so you might want to get into the weeds of it just a little bit further. And then Matt's probably looking at me, and I'll stop in a couple minutes. But basically, we provide all the data inputs that go into physics-based models. So we have physics-based heat models, physics-based flood models. We're going to run the stuff that a lot of you were doing today. WRF models for heat, right? Hydrological models that can route water efficiently at high resolution in urban environments. And then we take both the outputs of those physics-based models and all the inputs, and we train the MLs, the machine learning environments, of which there's multiple. And for those of you who are doing this kind of work, this is CNNs and combo LSTMs, because we want to be able to understand how it moves through space and time. Right? You need to know where the flood depth is at multiple points in time as well. We train that machine learning, and then we output this into a front end that tries to make it really accessible and where the data is downloadable. So here's just an example for heat. We're using the weather research forecasting model, and there's been a number of things that we've been advancing here. One is that we're doing this at resolutions that have very seldom been done, and certainly not at citywide scales. So WRF normally run around 1 kilometer or even higher. There's some applications that are 500 meter. We're running this at 500 meters for all the cities we're training on, and we're doing this at 100-kilometer bounding boxes. So it's a massive WRF model that we're running. We've completed this for Phoenix. We've completed this for New York. We're using that. We're training the ML right now. So I am talking about work in progress, but I'll show you a little bit of what the data is starting to look like. So that's kind of on the heat, humidity, wind, all the things that for the WRF folks knows what come out of there. And on the flooding, we're using two different surface flow models, both CityCat and HEC-RAS. CityCat comes out of Newcastle. We've used this for our work in multiple cities across the US. We're using HEC-RAS as well to train. That way the ML can learn from actually more than one type of hydrological model. So it's learning to kind of see what's going to work best in terms of the assumptions it's making. And so we feed in, again, all of that information. And then we provide outputs for not 2 scenarios, multiple scenarios. We're running 20 scenarios per city. After we've spent 3 years to get 2 scenarios for New York, we're running 20 scenarios for every single city that we're doing at citywide scales for all of this. And just as a little bit of teaser, these results just finished Thursday last week. So Giuseppe, it's a little bit for you. But we've run HEC-RAS in the South Mountain area, in South Mountain Village area, and are looking back at 2 interesting storms from 2014 when I first started collaborating with a number of folks here at ASU. This 1 inch of rain in an hour storm, and this is an example of some of the validation work we're doing as well, where we're providing various sources of information where we validate first the physics-based models, and then we have an entire validation phase for the ML models once we have the outputs from those. Here, one of the other storms we've been looking at, and you can see the model results in the middle, and then some of the potential ways that you can use various types of camera data or other data to try to understand where that is for the flood models. And then we output this into a dashboard at these high resolutions. And so there's probably a number of questions you might have. I've only got a couple more slides on this, but we're really excited because you're looking at real data in the tool. This is in Manhattan right now. This is flood data that's uploaded. It's actually, you can take a look at it if you're interested at dashboard.climateiq.org. But it's not just putting data up. This is deep ability to do on-the-fly analysis. So when you move around in this portal on the left, on the right automatically calculates and compares that flood risk in terms of the flood hazard data for any of those cells. And so we're using what's called an H3 system. It's this hex system, and it's basically nested hexes all the way down to 10 meters. And so you can get that information at any scale that you have a question about. And this is sort of automatically computing because all of the data is in there. We're building this API first. So this is part of how the data is being hosted so that you'll be able to take and download this data yourself and bring it into any other thing that you want to ask a question about. Because our goal isn't to make one tool to rule them all. Our goal is to provide advanced, scientifically and technologically advanced climate risk data that now you can use for lots of questions that you might have, including to ask questions about multi-hazard risk, right? So a couple outputs. Here's just one from the WRF models. This is the second round of our ATMO model. Here too, I kind of want to hold a contest on training, on naming our ML models, because ATMO ML is, I don't know, it could be sexier, right? And the same for our flood model for the ML, because there's 2 different machine learning environments for this. But I'm showing you this on the left. This is the WRF outputs, and on the right is the ML outputs. This is training on 1 sample, meaning 1 day in New York. We trained it once, gave us bad results. A little depressing. We did some model tuning, and we ran it again with just 1 sample, and we're getting, just visually, you can already see it's starting to represent the environment. This is humidity that we're looking at, starting to get the spatial pattern of humidity right in terms of the ML output. So on the right, in the little brackets, it says predicted. Just for New York City, we have 500 samples to train it on, and then we're moving to train it on lots of other cities. So it's going to learn really fast. Again, we got to see how all this works out, but we're feeling some confidence that this approach is going to produce really kind of amazing results when we have them lined up. The last thing I'll mention is that let's ask that question. Can we do 10 scenarios in 10 minutes for $10? I don't have the back of the envelope metrics on the cost here, but I'll run you through it. But let's just take these 2 types. On the left is WRF. The first thing that we've actually done is we put WRF in the cloud on Google HPCs for what we think is the first time ever. fully set up and run in the cloud so that we can really optimize that. And we decreased this from 95 days to run a 100-day simulation at this 100-kilometer scale at 500-meter resolution down to 8 days on the HPCs. So that's just running the physics-based model. The ML can do the same thing in 10 seconds, 5 to 10 seconds. So if you do that calculation, that's 1.5 million times faster than the standard, right? We're reducing the computation time down to nothing with this approach. With the pluvial flood model, it's not quite as fast, but it's pretty impressive that we can go from up to 24 hours to model on like a PowerPC. Putting this into the GCP, the Google Cloud Platform setup, we can reduce that down to about 2 hours per scenario. So it still takes a little bit of time, but it's relatively fast. Once the ML has learned that, and these are real tests, these are data from real tests that we've been running, now we're about 10,000 times faster, again, in the 5 to 10 second range to produce a new flood scenario. So it's almost on the fly. We think it'll get actually faster from there, so that not only can we produce all of these and upload these, but just like other AIs you've probably worked with, you'll be able to query it, and it's just going to give you the answer for any question that you ask it. Right? You can run any scenario. We're just training on enough of them, and it'll be able to interpolate for any of those other scenarios. So let me basically stop there and say that there's a lot of partners involved with this. It's a pretty ambitious effort, I would say, but I'm bringing it forward because I think there's some fundamental questions about how do we advance resilience in urban systems? How do we really start to harness the technology and the science together to meet the scale of the problem that we're dealing with? Happy to take some questions. There's a lot of people involved that I kind of need to thank, and I'm only putting up the names that are involved in the stuff that I showed you, from the Urban Systems Lab folks on the left to some of our funders, especially National Science Foundation, Google.org, and the City of New York for today. And we wouldn't be able to do this with a lot of Googlers. Folks who've come on from Google, who've worked full-time for us, in some cases 6 months at a time, fully on to help us build the back-end data pipelines, to help us do the engineering to put WRF in the cloud, HEC-RAS in the cloud, CityCAD in the cloud. So just want to thank you to that and say, finally, if we don't transform how we develop, how we make decisions, how we think about resource consumption in the city, I don't see how we're going to transform an urban planet for sustainability. The adaptation gap is really high, but there does seem to me, where my optimism is that the potential here in our science, as well as really harnessing technology, makes me think that we can actually understand the complexity of urban environments. So hopefully there's a couple examples here, and I'm happy to let you pick them apart. Thanks.